Hey everyone, so today we're going to do a quick review of integration, which is going to be integral to understanding the rest of Calculus 2. So integration is usually defined as the antiderivative. So let's go over what that means. So we say some function capital F of x is equal to the integral of f of x dx. So there's a lot of notation going on here, so let's figure it out. First of all, this horribly drawn symbol is the integral. If I drew it a little bit better, it looks something like that. It's kind of like an elongated S. And we define this as integration. And we integrate something called an integrand, which is some function. Here we're calling it f of x. The last important part is this last part right here, that sometimes people forget, but is actually very important. So this is called or at least describes the integration variable. So the integration variable here is x. And this dx you see is very much so related to dy dx when we introduce derivatives. So the x, as you can see is also here, is the integration variable. So we're integrating with respect to x. So that's going to be something that you should understand and that we'll go over later. And a normal notation you'll see is when we have some kind of lowercase function, we use the uppercase as the antiderivative or integral. So what this means is that f of x, or capital F of x, is the function such that if you take the derivative, you get back to f of x. So this is kind of nice if we imagine like some kind of chain. If we have f of x, f prime, and capital F, then to go up, you take integrals. And to go down, you take derivatives. dy dx. dy dx. So integrals and derivatives kind of undo each other, right? And that's what's shown right here. So that's something that's key that you should understand. And probably something you learned in Calculus 1 was the definite derivative. So right here, these are called indefinite derivatives. There's no bounds of integration. And what this means is you just get some function at the end of it. In fact, you actually get a family of functions, which we'll go over later. So something that you might have been introduced to in Calculus 1 was the definite integral. And this is kind of more fancy understanding that a lot of people know, which is if you have some function, f, and you want to find the area under the curve, so something like this, between a and b, this is defined as the definite integral, which looks like this, a to b of f of x dx. The definite integral and the indefinite integral are not the same, but they are very much so related. One just outputs a number. So the definite integral outputs a number, namely the area. The indefinite integral outputs a set of functions, but they're related. So we can actually write the definite integral as capital F of b minus capital F of a. What this means is, it is basically, if we do the indefinite integral of f, and we apply it at b and subtract where it's applied to at a. And that's how you get it. So that's the relationship between the definite and the indefinite integral. That's not obvious, but I don't think it's something we'll prove in this class, but you can search it up online if you would like to. And what you also might have learned, which we'll quickly introduce, is Riemann sums. So how this idea was found was they thought about how could you possibly calculate such an area? Well, if you take small rectangles, let's say like this, and you try to fit them together as well as you can, and eventually if you do enough of them, you can get all the way across. And the idea is, if you take some limit as the number of rectangles approaches infinity, then you get the sum of a bunch of small little areas of rectangles, the height of which is f of x at, like x0, x1, comma, times some small change in area that we'll just call dx, or delta x. So basically that's the idea behind Riemann sums. And if you're taking the AP test, you might be asked to do a Riemann sum with 5 intervals, which means choosing n equals 5 in this case. Honestly, it's really not that important to know, but it's an interesting thing to know how this idea came about. So now that we know indefinite and definite integrals are related, not the same, we should go over some examples of both of them. So let's do some examples of integrals. Let's start off with just the integral of x squared dx. So let's go back to our definition. This is equal to some capital F such that the derivative equals x squared. Well, hopefully this shouldn't be too hard if you remember the power rule. And so we know it should probably be something with x cubed. In fact, x cubed over 3 will do the job. And you can see if you take the derivative of that, you get 3 outside times x squared, and that cancels out with the 3 in the denominator. But hopefully you remember that we should be adding a plus c to the end of our indefinite integrals. Why do we do this? Because if you take the derivative, any constant term goes to 0. So technically with any antiderivative, there's always a possible constant term that we might have to account for. This is why it's an infinite family of solutions, because there's actually infinitely many antiderivatives. That's what the C stands for. You can choose any C you could possibly want to, given that it's some kind of constant, right? So hopefully that example wasn't too hard. In fact, we can generalize this. If we have the integral of x to the n dx, and this is going to be similar to the power rule we learned with derivatives, we're going to get x to the n plus 1 over n plus 1 plus c. And hopefully this is pretty clear. The n plus 1s cancel out, and you get n plus 1 minus 1, which is x to the n. Great. So now let's relate that to the definite integral. 0 to 3 of x squared dx. So how do we solve this? Well, like we said, this is just capital F of 3 minus capital F of 0. And usually this is written, I like to write it as something like this, where you kind of do this indefinite integral, and you get x cubed over 3. And you might be wondering why I removed the plus c. This is because if you're subtracting two capital F's, the c's are just going to cancel out always. So you can try that out, but c's will always cancel out when you're doing definite integrals, so there's really no point to write them in there. So this is what we have. And what this means is plug 3 in there, and then subtract it when you plug 0 in there. Luckily, when we plug 0 in, we get 0. So let's just focus on the 3. We get 3 cubed, which is 27, over 3 equals 9. And so to just understand this graphically, it would be, if this is x squared, then we're going from 0 to x equals 3. And it's this whole area right here, which is great. We know this is now 9. But what if I gave you a slightly more interesting integral? Something like negative 2 to 2 of x cubed dx. Now, if you want to, you can go and work it out. But I'll tell you right now, without even having to do any integration, the answer is 0. So, to solve this, it's actually faster to use our understanding of what the definite integral is. So let's quickly draw a graph of x cubed. It looks something like this. If you notice something, I wrote a negative 2 and a 2. What this looks like is something like this, right? You're summing up this area. But what you might notice is that it quite clearly is 0 because x cubed, there's a certain symmetry to x cubed, right? And we can talk about that in a second. What that means is that this area is the same as this. And since this is negative area, meaning it's under the x-axis, it's going to cancel out with this positive area. So we're just going to clearly get 0. This happens only when the lower bound is the opposite of the upper bound, right? The same would be the case if it was from 2 to negative 2. So this is an interesting property of integrals, and you should always watch out for this when you're doing certain definite integrals to make so this happens, because it's much easier to do it than calculating out a complex integral, right? And if you want to, you can actually do it and see that it'll cancel out. But why this happens is because x cubed is what's called an odd function. An odd function means f of negative x equals negative f of x. If you try it out, f of negative 2 per se is equal to negative f of 2. That means negative 2 cubed, which is negative 8, is equal to f of 2, which is 8, times negative 1, which is negative 8. So x cubed is odd, and this is always going to happen with odd functions. So that's an interesting example. And then there'll be one more example that I'll bring up. So first of all, we should note that this is an indefinite integral because we have 0 bounds. And at first you might be kind of confused because I've written this out and there's no x's, right? There's just a t. And you shouldn't try to overcomplicate these kinds of integrals because you will run into them. Since we noted that x is our integration variable, t we just have to pretend is some constant, right? In terms of our integral right now, t is a constant. So we're going to treat it as such. Think of t as some kind of number, like 5, 8, 22, whatever. So what this means is that we're just going to get tx plus c. And if you want to see how that works, well, if you take the derivative of tx, you're just going to get t. Same as if you took the derivative of 5x, you get 5, right? Same idea. So you should keep in mind what is your integration variable, and thus what values are constants, what values are actually functions. Because that's something to keep in mind so you don't get tricked up with an integral that looks like this one. So I'm going to hope to end off with just some basic properties of integrals. Properties. And these are really not too complicated, so try to memorize these, but they shouldn't be too hard. They're pretty straightforward. The first one is if you have an integral of k times f of x dx, where k is some constant, and that's clear from what we just learned, this is equal to k times the integral of f of x dx. So what this means is you can actually bring constants outside of the integral. And this is the same with derivatives, which is nice. And so an interesting example is if you have k equals negative 1, so you have the integral of some negative function like this, it's just equal to the negative integral of f of x dx. So that's something that can be helpful to clear up your math. Another property, which is similar to derivatives once again, is if you have some function f plus or minus some function g dx, this is equal to the integral of f dx plus or minus the integral of g dx. And what these plus or minuses mean is that if they're added, then you add the integrals. If they're subtracted, then you subtract the integrals. This is hopefully pretty clear, and it's the same from derivatives. If you're adding two functions, you can add their integrals, and you get the same thing. And then there's probably one rule you should learn about definite integrals that will be helpful. So usually when we thought of definite integrals, we think of a lower number, a, and a greater number, b, of f of x dx. So that we got something that kind of made sense, right? That it went from like here this way, like a to b. B was greater than a. Well, first of all, we should know what happens when b equals a. And hopefully you can understand that this just means that the derivative or the integral equals 0. I mean, you're basically integrating nothing, right? It's just a line. So that means the integral is 0, which is pretty clear. But what about when b is less than a? Because now you're kind of going the other way. Well, we define this as the negative integral. So what this means is that you can actually write it as negative the integral from b to a of f of x dx. So basically you can flip the bounds and negate the integral. And this is actually pretty clear when you look at our formal understanding of the definite integral, which was f of b minus f of a. And if you negate this, you get f of a minus f of b, which is the exact same as this and this. So hopefully that was pretty clear. You might see that we're actually missing some product and quotient rules here, and that's because there's actually not a really nice product rule for f of x times g of x. And this is partially why integrating can be really hard, because integrals are not always clear-cut as derivatives are. There's always a product rule, there's always a quotient rule, there's always a chain rule. Integrals are not that easy. Hopefully later in the year though, you'll learn a rule that we can deal with these kinds of products. They won't always be nice, but you can deal with them. Thank you.